Okay, welcome back to everybody. We have another exciting session, this time from the US. Now, our invited speaker is Alessandro Eltramari. He's a senior research scientist at the Bosch Research Technology Center in Pittsburgh, and he's an industry mentor at the Carnegie Bosch Institute, again in Pittsburgh. His interests are quite variegated: neurosymbolic reasoning for decision support, knowledge-based systems, learning algorithms, cognitive architecture, and so on. He has a long experience in developing ontology and building ontologies. And the reason to invite him was that at a certain point in the project, we realized it was not easy to see how you can connect the work in foundational ontology to work in data. And so we needed somebody that can actually understand both and see and explain how you can exploit both kind of knowledge and the technologies that are behind them. So this is what, if you want, is the reason to have him today with us. And in particular is, of course, going to talk about ontology, something that came out this morning again, the larger language models, and finally something we have not touched upon yet, which is neurosymbolic AI. And with this, I let Alessandro, maybe you want to add something more because this was a very short, but that's up to you. Please go ahead, and thank you for being with us.
Thank you, Stefano, for the nice introduction. Hello, everyone. On site and online. So I'm gonna then plan for 40 minutes, Stefano. Yes, no, I don't see.
Yes, that's fine. Thank you.
Okay. Cool. So you set the expectations already high. So now I have the task of showing you how foundational ontologies are used in some concrete applications. So I'll try to do my best with that. So just a few words. Well, again, I'm going to talk about a little bit, why ontologies and foundational ontologies in general are relevant these days, that are dominated by large language models. And I'll illustrate briefly a project that we have been working on with some colleagues here on traffic scene understanding, and try also to bridge that with the Industry 4.0 topics. Since we also have a little bit less time than expected, I just skip that. I mean, what is relevant also for this talk is that I worked with Stefano and the guys at the ISTC CNR Trento Laboratory for Applied Ontology for more than a decade, and I was also a co-author of Dolce back then. If you want to know more about what I'm doing these days, you just can Google Bosch Research Eltramari. You will find some blogs also that I wrote about what we do here, and we're still active in academic publications also. That can also be a source of information if you are interested. About Bosch Research, very briefly, in North America we have 3 centers. I'm in Pittsburgh. We work a lot here on human-machine intelligence, human-machine collaboration. So in general, the idea is to look at these topics from the perspective of smart environments, or in any case, we say situations where you would deploy sensor networks, so you have some information coming from the environment, and then from that information you have actually to elicit some intelligence, and from that intelligence understand different types of activities that are going on, or provide recommendation and so on. If I see this popping up again, I'll try to kill Microsoft Teams. In any case, we have also other offices around the world, and overall, I think we are around 1,500 researchers across Bosch, and 400,000 employees all around the world. Okay, so let's get started with the topic, right? Yeah, some context first, or at least this is, my view of the context. I think, when we look back at the past, in the mid 2000s, there was a split in the KRR community, applied ontology from one side and semantic web on the other side. At the beginning, most of the people kept collaborating, but however, over the years, this split became consequential. So there was a little bit more interest and funding in the semantic web, the formal ontology or applied ontologies. Semantic web is, definitely, as a community, as a kind of approach, is more application oriented. New conferences and communities sprang from this idea of the semantic web, thinking about ISWC, SWC, IEEE semantic computing. And then we started hearing a little semantics goes a long way, right? So there's the knowledge graph hype emerged among the other hypes, right? So, and you can see also from the right, so we go from the idea having well-defined ontologies. That is actually a little picture of Dolce, but of course there are other ontologies that also have been discussed, I think, these days, PFO and others. And then you start, having, a shallow semantics being used and being popularized through this knowledge graph hype. So we go to triples. Of course, we scale down a little bit the expressivity of the languages. And then fast forward to today, we have a situation where, foundation models arose. And also this idea of neurosymbolic AI. And so from knowledge graph, so again, which is still, an explicit representation of knowledge, like ontologies, but less expressive, we go into, underneath, I would say, underground, in a situation where you don't have any more, I would say, explicit knowledge represented, but you talk about embeddings. So you talk about, vectorization, latent semantic representation, let's say, of explicit knowledge. And then this is very relevant because, of course, you go from a situation where you have a large representation of knowledge that can be, for instance, Wikidata, can be the Google Knowledge Graph or other things like that, to embeddings that talk the language of neural models, so to speak. And so these can be used to let's say, induce in these models a little more contextual, latent semantic representation of an environment or a situation or activities that are occurring, structure on top of data that again are reduced at a sub-symbolic level and so on. So and why people infuse knowledge graphs and so use these knowledge graph embeddings with neural models, because it's been proven empirically, if you look at the state of the art, that this can help performance across different tasks, from perception to language understanding and so on. Again, without providing too many details, but still, trust me on this. What you see in the state of the art is that even with these embeddings, when you use the neural model, I don't know, for understanding, for instance, applied for autonomous driving on other applications like that, you see that these, even when you infuse knowledge, you still are, end up with a system that is insufficient for robust reasoning. Spatiotemporal, for instance, if we talk about, again, mobile system, robots, or even high-level activity recognition that uses stationary cameras as input of data. Or when you look at language models, you see that this language model seems to be very robust, seems to be very credible in a sense, but then when you probe them a little bit more, you see that they are missing some elemental aspects of analogical reasoning, temporal reasoning, common sense reasoning, and so on. Right, and these days, actually, these days, meaning the last year or so, there is an increasing number of publications that use it, that points at using more expressive constraints. So back to the old-fashioned, I would say, AI in a sense, axioms, rules, to enhance these reasoning capabilities and also help constraining when we talk about not only neural models in general, but large language models like ChatGPT, help constraining their misbehavior and hallucinations in some cases. So, the question that I have then, and the community, I think, these days is having is, has reader semantics reached the end of this long way? So are we already, beyond this knowledge graph hype? So, and then, neurosymbolic AI is really the new thing, say the new, so it's not new because as people that have been around for quite some time know that neurosymbolic AI, the first works that consider they use this label date back to like 25 years ago, and so the community was very small. But then these days, actually, if you look around you see a lot of systems that are neurosymbolic in nature. I think most likely, the most famous example is when you do a Google search and you see on the right, for instance, these little snippets of content. That result is coming through the combination of the Google Knowledge Graph, which is, as you see there in the slide, pretty big, with the Google ranking algorithms that combine different type of models in order to provide that type of ranking. And of course, these days it's also powered by language models. But aside, from what the big giants are doing, if you look at the state of the art, this is a very recent paper that won the best paper award at IJK workshop on safe learning and race. Is about autonomous driving, but has been republished recently on machine learning, the journal. So it's about basically using constraints and rules to mitigate the errors made by neural models when they are deployed to classify objects in real environments. For instance, in the snippet that you can see here, rules are used to block situations where a perceptual neural network has classified a traffic light as both red and green at the same time. So you put rules in the downstream of this classification to basically correct mistakes done at the level of perception. And so this is actually just a little slide to show you, that what I said around, the fact that neurosymbolic AI is gaining more and more momentum. You see the number of publications going up. Recent book, edited book by Pascal Hitzler, where also we have a chapter there that tries to summarize a bit the state of the art these days. A new journal on the bottom left. I think the first issue is planned for not Q1, as you see there, but actually Q3, and so on and so forth. And also, of course, industry. IBM as the largest neurosymbolic AI group that I am aware of, at least. NVIDIA is investing a lot there, Alibaba, and also we have a team in Bosch across Germany, US, and China. So the current questions around AI can be summarized a bit as these ones. At least, these are the most frequent one that you will find around. So, do large language models understand the world? Are they really intelligent, or are they stochastic parrots? There's a little animation that I forgot about. And can we trust the output of large language models? Can we make AI sustainable? Will AI destroy us? Will AI steal our jobs? So today I'm gonna just talk about the top part of this figure, and I put there, a few references of that are kind of very well cited these days on stochastic parrots. Comes actually from that paper you see in the title on the top right. The fact that are these models really learning how we understand the world, or are they just learning how we talk about the world, and therefore they don't have any grounding with the world, which is if you want already a sort of answer to the question at the left, if the LLMs understand the world or not. And there is a paper about all the failures that people have recorded so far, and also the trustworthiness of these models. Can we use them? Can we just use them, trust them, and forget about human in the loop kind of technologies, and so So, right, and so some examples, right? I talked about earlier about that, when you look at these large language models, yeah, they are impressive. They display a lot of linguistic competence, but then when you probe them, they make a little bit of you can actually see failures across the board in very trivial situations. And so actually, this is a paper article that was published last year, I think, in the MIT Technology Review. And here are some examples, right? So, for instance, analogy. So, all the examples that I'm going to show in the next 5 minutes are actually taken from real data sets, question answering data sets in particular. And there are also papers that I refer to at the end. So this is not just the usual. Okay, let's do an anecdotal example. So let's probe with one question if the model fails or not, and then let's go on LinkedIn and make a nice post about how bad language models are for AI and for the world. So these actually are data sets of 20, 30, 40,000 questions and answers, which have been used to evaluate comprehensively and rigorously these models. So the examples that I showed today are just the tip of the iceberg, but an evaluation done scientifically speaking and published in different conferences has actually displayed these kind of problems, not only on individual examples, so-called. So here is just one type of problems that we see when in analogy. So when you ask, is there a vegetable is about as big as your head? And then you see ChatGPT giving you like a ranking: pumpkins, cabbage, eggplant, watermelon, so everything that has a round form. But then if you change a little bit the question, what part of the human body can be compared to a pumpkin, then ChatGPT starts to give you explanations about the fact that you should not make any comparison between human bodies and other things. Of course, this is a paraphrasis of the previous question, and a system that is capable of understanding the conceptual model behind the question should also be robust to paraphrases. And so this is another paraphrasis where, for instance, we ask what part of the human body is as big as the pumpkin, and aside from the paragraph that says it's not appropriate, ChatGPT has also, there is no part of the human body that is as big as a pumpkin. So the first answer at pumpkin in the first place, here actually ChatGPT is saying, even though it's an ethical problem to make this type of comparison, I assure you there is no part of the human body that is big as a pumpkin. So, okay, in contradiction. And then again, same thing. We change a little bit the nature, the question: what part of the human body is about the size of a pumpkin? And then we see the same type of question, the same type of answer. Temporal reasoning. This is a paper published a few years ago about this data set, Bobby from Facebook. So without going into the details here, also because I don't want to run out of time for the rest of the talk. What we show here is that when you think about a timeline and you put the days of a week there, and you have a relatively complex description of everybody's agenda, ChatGPT is not able to understand that somebody is not available on Thursday or Friday, or that Thursday is before Friday, and so on. Spatial temporal reasoning as well. So this also comes from a data set, the same data set, Bobby, that is subcategorized through different type of questions, these spatial questions. When you have something like the triangle is above the red sphere, the triangle is to the right of the blue square, and then you have a bunch of questions that ask for the positioning of the red sphere. And of course, there are things that can be said about, if is something on the top, is the square on the top at the left of the red circle, or at the top left. These are subtleties, if you want. But what you see on the right, which is the output of ChatGPT, is that ChatGPT denies any capability of even making hypotheses about finding the position of these objects. And humans, which is actually the result that you can see here, yes, no, no, yes, yes, those are human answers from human annotators, typically can understand what is going on in this type of scenario. So what's the answer to this problem? So we see that reasoning is not that robust in these large language models that again are designed to understand surface level characteristics of language, but not the deeper conceptual connections. And then somebody, actually, I found this a few days ago, said, okay, well, let's add ontologies so that this is the recipe for success. But not so fast, I would say. So first of all, what does it mean to add an ontology to a large language model? So mainly it means fine-tuning. So fine-tuning is this process where you basically adjust and adapt a pre-trained model like ChatGPT or others, Bard, Llama, or even before that, BERT was the first large language model from Google, to perform a specific task or to cater to a particular domain more effectively. And so basically what fine-tuning is, you have some like a smaller data set, use that smaller data set to focus the large language model into that particular domain. So, but can we use ontologies for fine-tuning? And not really, because you need scale, right? And then an ontology typically, is not so big. You have a few classes, and those classes, of course, can be instantiated. But the order of magnitude that you need to successfully fine-tune a large language model is beyond a T box. You also need an A box, right? So the instances of the ontology. And so then, we are asking ourselves, and not we as Bosch research, but in the community, specifically in neurosymbolic AI community, how about using, well-defined ontological principles derived from foundational ontologies to generate a knowledge graph and then fine-tune large language models with it. So, and here actually is an example of what we have been doing in this space. These are some of the contributors to this project. We also collaborate with University of Southern California in this case. Hezan Kazemi, you see on the bottom right, has been an intern for me for a couple of years. And then I have Jonathan Francis and Isul Mehdi from Germany that work in this project, and Philip Ilieski and Aravinda. So Philip also was the supervisor of Aravinda and Hezan in their PhD. So what is the problem that we are trying to solve here? So if we look at the present of video, so the capabilities of video AI, used for video-based activity recognition. So you can see, a little bit here what is the limitation, what are the limitations, so that if you develop, and even if you look at the state of the art, you don't have to think about proprietary algorithms as part of this, but even state-of-the-art computer vision, it's very easy to find systems that do pretty well object recognition. So there are car, trucks, pedestrians, or attributes of these objects like their speed, their trajectory, even prediction of trajectory, of course. You can even infer, if you look at the scene and you see many cars there, you can see, okay, this is normal traffic situation, or this is more like traffic congestion, or even basic behavior, right? So you can measure the speed of a car and then say it's above the limits, or you can recognize basic behavior like collisions. But what is the future of video then, which is where we are trying to develop a solution for at this point, is more high-level context understanding. So going from object level understanding to event or behavior level. So for instance, garbage trucks. So it's very expensive to train a classifier to recognize garbage trucks. Expensive because you have an infinite, I would say, source of data for trucks and good labels for trucks. But a garbage truck is something a little bit more different, which appears more rarely in data sets. Although if you look at a garbage truck as a type of truck that behaves in a certain manner, so makes regular stops at each block, at least in the US, and then there is a person co-located with the trunk or with the rear of the truck, and this person tends to often on the truck and grab other objects, in this case trash bags. So if you stitch all these elements together, and of course this requires high level reasoning, then you can actually infer with this rule, if you want, you can put together a rule, infer that the behavior of this truck, where the label truck comes from computer vision, can be used to infer that this is a garbage truck. So then at that point, you can go back in your data, run this rule, and derive garbage truck behavior from the data set. So this is an example of what behavior means. But other more complex behaviors are, for instance, criminal activities. If you want to understand if somebody is stealing a car from a parking lot, it's not that you cannot do that only from one frame. You need to track that person over time. So this is very challenging for systems that are only based on perception, and therefore systems that use convolutional neural networks or this kind of neural architecture to, again, that are trained over data from cameras like this, or for self-driving cars or ego vehicles, so-called, and so on. And so in this so to address this problem, we built an architecture that we call HANS, and I don't have the. What is important here is that what we developed, which is represented in the light and the dark blue boxes, is we developed a representation of the traffic domain knowledge, and on top of it, we use a foundational ontology. I don't want to go into the details of the human in the loop, but pretty much human in the loop here is just a fashionable way to say humans were involved in defining the links between the foundational ontology and the traffic domain ontology, and also to actually expand a little bit the vocabulary, because of course everybody drives and everybody knows the entities that you can find in a traffic scenario, but you also need to align with public resources. You want to align with the typical metadata schemas that are used by traffic agencies in the world to describe these entities, to assign geospatial information to these entities, and so on. So that's why the human was in the loop there. And then we take this knowledge, and again, this neurosymbolic AI fashion, we fine-tune models. We tried a few ones, and today I'm going to just describe one. To basically perform, so to induce this knowledge of the domain into the model and let the model basically perform this higher level reasoning. And where the goal is, again, to classify higher level behavior. And we filed, so we have actually a few patents pending right now in the US with this architecture. So when you see here foundational, right? So what we mean here is actually Dolce aligned with actually what is missing there is SSN, the semantic sensor network ontology from W3C. I just put W3C. So of course, no need to go into the details of what Dolce describes and represents. SSN also should be well known, but is again an ontology that uses actually some primitives from Dolce and other ontologies to describe information perceived by sensors, and how the content of these perceptions can be represented using classes like events, quality region, and so on. So we actually started from this to develop our own traffic scene ontology. Although, I mean, we were not kind of bound to use the same standards in this case. We wanted a solution that was, adequate to our problem. And so we revisited a little bit the Dolce SSN alignment as follows. So you see that picture on the left. So we use this notion. We introduced this notion of atomic scene, complex scene, observation, and so on. So from that picture, basically what we have is one atomic scene, two observation, one time instance, two objects, two color qualities, and one color quality region, which is black. So let me explain what I mean here. An observation in this alignment is a property of an object at time t. An atomic scene is the collection of all the observation at time t. So here we have two cars, we are observing two cars. The atomic scene collects the observation of these two cars. They share the same timestamp because, again, an atomic scene is atomic, so it doesn't occur in an interval, but only in an instant. A complex scene, however, is an arbitrary collection of the atomic scenes over a given time interval. So suppose that I have two subsequent frames where these two cars move slightly. And so if I stitch together these three atomic scenes together, so this one that you see here plus other two, I have an arbitrary collection, which is a complex scene. What is not arbitrary is the video. So a video is the collection of all the atomic scenes that are relevant for a specific dataset, for instance, and whose start coincide with the start of the video. So the first atomic scene timestamp coincide with the start of the video, and the final atomic scene timestamp coincides with the end of the video. So the Dolce's heritage, as you can see here, is actually in a few things. Of course, we made a few modifications, but again, the inspiration is that from Dolce. So objects have direct spatial qualities, so the black of the car. Observations, atomic, complex scenes, and videos, which are, closer to SSN. Still, these are, I would say, perdurance, and they have direct temporal qualities. Then we have this relation of composition and inclusion, which at the end of the day is really a temporal proper part, if you look at the Dolce's axiomatization. And then, another characteristic of Dolce is this distinction between the qualities and the quality values in the quality spaces. So here we can, of course, for black is not that useful, but when you think about, for instance, let me see if I have it here in this one. Later, if you have the speed of the car, then you have the individual speed of that particular car, which is distinct from the value of the speed, which is in the quality space. So an example, a little bit of this representation. Let me add. So from the top to the bottom, you go from the top classes to the instance level. Again, here I'm saying winking at Dolce through SSN, because this is not traditional Dolce, not even traditional SSN. But you can see at least a little bit the flavor of the foundational ontology, Dolce, and SSN as a core ontology being displayed in this slide. And so basically what we are interested in the core part, a camera is a type of sensing device associated with a scene that includes the position of a car, so car participate to position, and the car is located in a spatial region, and you have a distinction between centroid and geolocation depending on relative geometries, if you want to represent space as a relative geometry or as absolute GPS coordinates. And then you have the instance level when you have a specific camera that has a specific associated with a specific scene. Here I'm not making a distinction between atomic or complex. And there's different participants, and those participants are located in different regions of space. What we introduced that I am not fully sure that is consistent with Dolce is this notion of having events interpreting. So actually, this is what I introduced before. So this compositionality between atomic scenes and complex scene. But what I meant is this actually. So the events here being interpretation of scenes. So you can think of events here as general properties that you can assign to these spatio-temporal entities that are observations or atomic scenes or complex scenes, depending on the granularity. So with the intuition that if you look at an event, so if you look at these spatio-temporal entities, you can assign them properties depending on your perspective or context or criteria. So the same spatio-temporal entity can be a traffic congestion, or can be also seen as a rush hour. Rush hour in a city is, of course, comparable to a traffic congestion, but is defined by the fact that there's a particular time interval in big cities where traffic congestion occur. So depending on what you need in your system in a downstream task, you want to have these properties being defined at a level that is substantially distinct from the level of spatio-temporal representation of atomic scenes, complex scenes, and so on. And this is actually a nice representation of this made by colleague Anis. So there are details about this that I don't like. The fact that you can look at you see here the compositionality, the atomic scenes made complex scenes, and then a complex scene can be interpreted in different ways depending on how you look at it, depending on the property you want to use to represent this intentional, with the S, the intentional aspects of these complex scenes. However, one can say, okay, if you see a traffic congestion and inside that traffic congestion there is an accident, then maybe it's not really the same complex scene that you are applying the property to, but are just compositional also in nature. So within the congestion, you can see an accident, but you can actually pinpoint that accident and distinguish that from the rest of the complex scene. But these are details. In the way we are using it, we are trying to have a clear-cut properties. And how we are using it. So we are using it in this data set. Of course, we use it also with the proprietary data set we collect with Bosch, but because we want to publish, we want to be out there and show our solutions and share our solutions.
Sorry to interrupt. If you can go to the conclusion, please.
Yes. Well, give me at least 10 minutes because then I can, and then we can 5 minutes of questions, and that's it. Right. So we use this data set, intelligent with the traffic UA is called, where you see a lot of scenes and you have different categories of questions, and then you have to be able to answer to those questions. So you have to create a system that is capable of understanding what is going on at the road, what may be the reason for an accident, and even to do things like event forecasting or counterfactual reasoning. What might have happened moments ago when you see a particular scene. So what we did basically is, and I can actually show this very quickly, we developed a system that, first of all, we took the data from the camera, we instantiated this traffic scene ontology with this data and created a knowledge graph. From the knowledge graph, we came up with the Sparkle queries that represent the question in the data set, and then ran these queries on the knowledge graph and extracted tables that represent the answers. From these answers and these questions, what we did, we translated everything into natural language, and we fine-tuned a model, in this case a visual language model, to perform question answering using the video and text-to-video search. So the only thing I want to stress is, how you do go from knowledge graph and ontologies to language. Well, we use, something called verbalization, where basically it can be done in 2 ways. One is through templates. So suppose that you see something like that in the knowledge graph. A car has average speed, a certain individual speed that has a value of 5 meters per second. So you can come up with a template, and you can do it for many types of patterns like this, that says, if you have the property average speed associated with the speed of car, then you can output a sentence like car 23 is moving at average speed 5 meters per second, where in the inbound lane, which is the location. You can do it with templates. That's what we did, but you can do it also using large language models fed with knowledge graphs that can output natural language, as you can see in the snippet code that I generated in like 3 minutes using ChatGPT. So we did that. This is an example I can just gloss over using a Sparkle query to define the directions of different cars in a data set. And again, as an example of querying the knowledge graph, extracting the answers, generating the sentences, and fine-tune the model. And this is a table from those. So without going into the details, because we don't have time, what I can tell you is that when you take the baseline model, the frozen one, meaning that there are different layers, because it takes time to fine-tune all the layers, we froze the model and we only took a few layers of the neural network. So the baseline, so no knowledge infusion, has an accuracy of 32.1%. When we infuse the knowledge, we gain 9%. And actually, this gain has been done in one shot. We didn't optimize anything. So this shows that when you infuse knowledge that comes from very well-defined ontology-inspired principles on top of knowledge graphs, you can actually gain a lot in terms of the spatial-temporal reasoning capabilities, which you can see here. Right. So I'm going to gloss over this because I already said what is in the conclusions. We embed, let's say, in natural language format, some of the Olcz's axioms, not all of them. We didn't experiment on using other foundational ontologies to do this type of infusion, but this would be a good project for a student if anybody is interested in this. Related work, I think, is important that we are not just proposing these like some crazy guys from Pittsburgh, but you see around that this is a new type of trend. This is a system, Deep Onto, by Ian Horrocks at Oxford, that takes high-level axioms and tries to verbalize them to create something like sentences that contain foundational ontology axioms like based on quantification, based on the semantic relation like part of, and so on. So you can find that it's still to be published, but the system is already available on GitHub. And this is actually Stephen Stubb, his group, working also on traffic scenes, similar approach, but using graph neural networks. The last thing that I'm going to show you is that why is relevant for Industry 4.0? Well, because if you look at situations where high-level reasoning is important for scene understanding, then you can see here that if you have a system that like an autonomous pallet truck going around, and then it sees something like this, but then typically we know as humans that a person follows as a pallet truck is manually operated, but only based on perception. You don't see any human here. So this is the importance of when you, for instance, develop autonomous systems for smart environments, you need to endow them also with knowledge. You cannot rely only on perception. And this is why scene understanding in traffic situations can actually be transferred to many other domains, like, for instance, Industry 4.0. This is an example. Again, I don't want to go into the details of a system that operates on a manufacturing plant and is applied for machine monitoring. When you can actually devise a set of rules based on the representation of what the agents are doing, what type of activities they are performing, who are the participants in those activities, and what are the constraints that you can apply on top of this domain. Yeah, so this is my last slide. Again, the takeaway message is that large language models are far from perfect, and rigorously representing the world is what ontology are designed for, and they are coming back because people are realizing that with triples there's only so much you can do. We are seeing in the results that embedding knowledge graphs into large language model through verbalization improve the performance. We are starting to see how we can add a delta on top of these improvement using foundational ontologies and axioms or rules derived from those. And some examples that can be of interest for your community or for this project, OntoCommons, are, for instance, machine monitoring, process optimization, security, surveillance, resource management, and so on. So thank you, and I'm open for questions.
Thank you, Alessandro. Very, very interesting. Let's see if we have some question to. Can you check online also?
Yes. Okay. Just nothing.
Okay. Anybody that wants to give a shot from the audience? Oh yes, please.
Oh yes. Oh my God. What does that mean? Thanks for the presentation. I'm not much an expert in neurosymbolic AI. I was wondering if you compared your methods to graph embeddings. There are some developments in graph embedding and computing similarities, and if you used parts of that into your pipeline, or if you compared results with that.
Right. No, that's a good question. And I gather that you mean knowledge graph embedding.
For example, yeah. So
Yeah.
yes, graphs are graphs, but graphs embedding, yeah.
Yes. So we are actually preparing right now a paper that has this nice table that my student this year is putting together, when we compare different embedding methods with our method. So including TransE, OLE, mode-to-vec, all these type of algorithms. Now, of course, I think you mentioned what you can do with the embeddings is just looking at the embeddings, you can measure the similarity. Okay. And so with that similarity, you can learn a lot about the events that you are representing, for instance, in the knowledge graph, and then they are translated into the knowledge graph embeddings. What we do, though, is a little bit orthogonal, if you want, because with these knowledge graph embeddings, what we do is basically going back to explicit representation by verbalizing the content of the knowledge graph, and use as model a large language model or a video or a multimodal, so visual and language model, so that uses both input, vision, and language, to perform a downstream task that in nature is question answering. So we are very much constrained in our evaluation by the downstream task, which is a system that you can interact with and ask questions like, is there an accident here, and or was a pedestrian involved in the crash, or is there a near miss in the scene recorded yesterday by the stationary camera over the intersection? And so it's not easy, it's not straightforward to do a comparison only at the level of similarity and knowledge graph embeddings, unless you are able to represent every type of information, both the information at the linguistic level and at the level of the scene. So I don't know if that was clear, but evaluate.
That's clear. That's and also very nice. I was thinking, because language model, visual model, they usually give you some predictions. And with such a graph embedding, you might use it as at least some sanity check to verify that those predictions actually are not really far from what you also have in your data, in your knowledge graphs.
I see. Okay, and this is another element of our system, which I don't have the time to show, but from the embeddings, we can actually. So, for instance, if our model, neurosymbolic model, chooses the answer in the traffic QA dataset, yes, there is an accident between these two cars. We can actually look at the embedding and extract from the embedding the knowledge, explicit knowledge, that the model has attended to answer that question. So in that sense, we look at the embedding space, and from the embedding space, we can understand better. So we go towards explainability. What is that the model used to answer that question? And we can actually understand if the model uses the knowledge, but the correct one or not. Because if the model has used not the correct knowledge, of course, is an additional problem, which is not a problem of the knowledge graph, is a problem of the infusion mechanism. And for that, we can actually use other embeddings to have that type of signal to compare with, in terms of at least the visual ground truth.
Thank you.
Thank you. I think we should now close. I have a short question, if I may, since I have the authority, take advantage of that. So we have been discussing yesterday, at least I pushed for the comparison between ontologies and the consequences they have in application. Now, I wonder, here you use Dolce for good reasons, if not for others, because it gives you this cognitive approach that helps in the explainability of what you see in interpretation. But I was wondering, would that make a big difference if you use another ontology, maybe with another approach, I don't know, maybe a 4D ontology, or would you say that some are more apt for this kind of application in this neurosymbolic approach?
Yeah, the short answer is that we don't know. I think I had like a one line in my conclusion, is that we work with Dolce, but not only because of Dolce or because I want I push my hand on the table and say, okay, let's use Dolce, because Dolce has been aligned with SSN, which is exactly a core ontology used to represent sensor-based information. So it was very well motivated what we did, but it's an open question. We don't know if by using another foundational ontology and another model to represent events, for instance, 4D representation rather than 3D, we see any change in the downstream task. So this is an open problem, and I would really much welcome somebody that is interested in working in this area. So yeah, the short answer is that we don't know what are the effects of that. It would be interesting to know, right?
Okay, thank you. Very interesting talk, and a lot of new questions and ways to use the foundational ontologies. So I hope even people working demonstrators are now convinced that there is an advantage on studying or at least using those more complex modeling systems. Thanks a lot, Alessandro.
Thank you, and enjoy the rest of your convention. Yeah.
Thank you.
Bye-bye.
Bye.